So I want to do yet another sequence limit because the technique that's used here is something that's going to be very, very important later, a little bit later on in the chapter. So I thought it would be useful to just cover now how to do this. So the problem is to find the limit of the sequence 1 minus 1 over n to the n for n greater than or equal to 1. This makes use of the very important technique that a to the b is equal to e to the b ln of a, except of course instead of a and b being constants, we're really going to see them as functions here, or at least variables. So here what you notice is that you have the kind of unusual L'Hopital's rule form, which is 1 to the infinity. We all know that L'Hopital's rule includes it covers situations where the limit where substitution leads to 0 over 0 or infinity over infinity, but there are some lesser known cases, such as 0 times infinity, because that can easily be converted into either one of these two top forms. But less obviously, well, actually, there's another one that we don't see very often, which is infinity minus infinity. And then this example is going to be 1 to the infinity. If you notice that as n approaches infinity, what I have is 1 minus 0, which is 1, and then n goes to infinity. It's a little less obvious why 1 to the infinity is a L'Hopital's rule form, but it becomes a little more obvious once you realize how this transformation works. So that's what we're going to do. So in any event, what we want to do is, since the only type of limit we can find is the limit as n approaches infinity, we want to evaluate the limit as n approaches infinity of 1 minus 1 over n to the n. So that's going to equal, using this transformation that you see here, that's going to equal the limit as n approaches infinity of e to the ln 1 minus 1 over n to the n, because e and ln are inverses of each other. So if I take e to the ln of something, I just get back to something. And now I'm actually going to convert it into this form. This is going to be the limit as n approaches infinity of e to the n times ln 1 minus 1 over n, just using a law of logarithms that says that ln of a to the b is equal to b times ln of a. I'm just doing that in that step. Okay, so now what I need to do is I'm going to rewrite that limit. You notice what I have here is I have n approaching infinity, so this is going to be infinity times ln of 1 minus 0, so it's going to be ln of 1, which is 0. So I have an infinity times 0 limit. That's like this sort of strange L'Hopital's rule form. So what we're going to do is we're going to convert this in this way. This is going to be the limit. Let's get back to my green pen. This is going to be the limit as n approaches infinity of e to the ln 1 minus 1 over n over 1 over n. All I'm doing is saying is that multiplying by n is the same thing as dividing by 1 over n, right? In other words, n is equal to 1 over n. That's all I've done here. Sort of putting my side comments off that way. So, okay, so this is now, what I have now is I have the natural log of 1 minus 0, so in other words, the log of 1, which is 0, and then 1 over n, 1 over infinity is 0. So this is, in fact, a 0 over 0 limit. That's exactly the type of limit that I need for L'Hopital's rule. So this is going to equal the limit as n approaches infinity of e to the, this is going to be 1 over whatever's inside here. It's going to be 1 minus 1 over n, and then times the derivative of 1 minus 1 over n. That's actually, I know that we're not used to doing derivatives in n, but like I said, we weren't going to make a big deal of converting to x's. So this is going to be negative, sorry, no, this is going to be positive 1 over n squared. In other words, the derivative of negative 1, of 1 minus 1 over x, because the derivative of 1 is a constant, and this is like negative 1 over x, that's just going to be positive 1 over x squared. So we'll add that to the side work there. And then I want to make this e a little bit lower because I need to make a really big exponent. The derivative, of course, of 1 over n is the same thing. That's going to be negative 1 over n squared, like that. So what I now have is this is equal to the limit as n approaches infinity of I have 1 over 1 minus n to the, 1 over 1 minus n, and then these terms here, I have 1 over n squared divided by negative 1 over n squared. That's just going to be negative 1. So this is going to be, let's see, e to the 1 over 1 minus 1 over n times negative 1. So in fact, I can really just put the negative here, and that gives me, that's the simplified expression. Now I can simply take the limit as n approaches infinity. This is equal to e to the negative 1 over 1 minus 0, which is equal to e to the negative 1, or 1 over e. There we go. By the way, I just want to point one thing out. Technically, before I could apply L'Hopital's rule, I was really supposed to, and here's where I applied L'Hopital's rule right there. Technically, what I was supposed to do is I was supposed to take this limit and bring it inside. I was supposed to actually put it in the exponent by the composite limit rule. Again, we've all covered limits. I don't want to be too fussy about that at this point. I just wanted to demonstrate how L'Hopital's rule was used in this case. This is a fairly important point. This is a type of calculation that you should know how to do. And by the way, I just want to point something out that in general, that not in general, but it's also the case that the limit as n approaches infinity of 1 plus 1 over n to the n is equal to e. So that's a fact that you can demonstrate in pretty much the same way that I did here. It's worth going through that exercise. And if it's 1 minus 1 over n to the n, then you get 1 over e.